Assalamualaikum warahmatullahi wabarakatuh. My name is Nick Fazarul Hakim bin Kamal Zuki. My metric number is CD240138. So now I want to share about introduction about our project, which is improving the performance of gas turbine power plant, which is BRAYTON cycles. Okay, for gas turbines are used in power plants, aircraft and industries. They are popular because they produce high power, start quickly and operate flexible. The compression. Air is compressed in the compressor, increasing pressure and temperature. Heat addition. Fuel is burned at constant pressure in the combustion chamber. The third one is expansion. Hot gas expand in the turbine to produce useful work. For the last one is heat rejection. Remaining heat is released to the surrounding. Next is real cycle loss. Okay, for the point number 1 is real gas turbine do not operate ideally. Point number 2 is loss occur due to friction, heat transfer and pressure drop. Point number 3 is these losses increase compressor work and reduce turbine power output. Okay, next we go to the key performance factor. Point number 1 is pressure ratio has an optimum value to hide increased losses. Point number 2 is turbine inlet temperature. Higher temperature improve efficiency but is limited by materials and cooling. Point number 3 is performance improvement method, which is we use regeneration, intercooling and reheating.
Assalamualaikum, my name is Muhammad Nazrin Azimi Anwar and my matrix number is CD240142. Okay, today I will explain the literature review related to our project. Based on previous study, gas turbine power plant operate using the BRAYTON cycle. The BRAYTON cycle is a fundamental thermodynamic cycle that is widely used in a power generation as well as in a propulsion system. Such a aircraft engine, in a terms of cycle operation, the process begins when atmospheric air enters the compressor. The air is then compressed to a higher pressure and temperature. After that, fuel is injected and burned in the combustion chamber at a constant pressure. This combustion process produces high temperature gas. These high energy gas are expanded through the turbine to produce mechanical work, which can be used to generate electricity. Overall, the BRAYTON cycle is known for its simplicity, reliability, and suitability for high power application, making it an important reference for our project. Okay, next is regeneration. What is regeneration? Regeneration is a performance improved technique that involves recovering waste heat from the turbine exhaust gas, and it is using to preheat the compressed air before it enters the combustion chamber. This is achieved by installing a heat exchanger, known as a regenerator or recuperator, between the turbine outlet and the compressor outlet. By preheating the air, the amount of fuel required in the combustion chamber to reach the desired turbine inlet temperature is reduced. As a result, the thermal efficiency of the cycle increase while the specific fuel consumption decrease. Regeneration is a particularly effective for gas turbine, operating as a low moderate pressure ratio where the turbine exhaust temperature is significantly higher than the compressor outlet temperature. Okay, lastly is reheating. Reheating is a technique used to increase the turbine work output by expanding the working fluid in the multiple turbine stage with heat addition between the stage. After partial expansion in the first turbine stage, the gas is reheated at constant pressure. Before entering the next turbine stage, this increases the average temperature at which heat is added to the cycle and allow for greater expansion work in the turbine. As a result, reheating improves the power output of the gas turbine system. However, reheating also increases fuel consumption, which may reduce the thermal efficiency and it is not properly optimized. For this reason, reheating is commonly applied in application where high power output is more critical than fuel economy, or when combined with other improvement techniques.
Assalamualaikum, my name is Muhammad Daniel bin Muslim, nombor matrik CD230272. Today I want to discuss about our project design. First is system description. The gas turbine power plant analyzed in this project operate on an actual Brayton cycle and represent a simple open cycle gas turbine system. Ambient air is first drawn into the compressor, where it is compressed to a higher pressure and temperature. The compressed air then enters the combustion chamber, where fuel is injected and combusted at approximately constant pressure, producing high temperature gases. These gases expand through the turbine, generating mechanical work. A portion of the turbine work is used to drive the compressor, while the remaining work is delivered as net power output. Finally, the exhaust gases are discharged to the atmosphere. Due to non-idealities such as irreversibility, friction, and component inefficiency, the actual cycle performance is lower than that of ideal Brayton cycle. Next, this is diagram for our project design. This figure represents a gas turbine power plant operating on the Brayton thermodynamic cycle. It shows how airflow continuously through the compressor, combustion chamber and turbine, converting fuel energy into mechanical work and electrical power. Each component is the figure correspond to specific thermodynamic process in the Brayton cycle. For the compressor, air enter at ambient condition. Pressure and temperature increase, and the thermodynamic process is isentropic compression, state 1 to 2. Next is combustion chamber. Fuel is added and burned. Pressure remains nearly constant. For the thermodynamic process is constant pressure heat additions, state 2 to state 3. Next is gas turbine. Height, temperature, gas expand, produce mechanical work. For the thermodynamic process, it is isentropic expansion for state 3 to state 4. Lastly is exhaust or heat rejection. Exhaust gases are released to the atmosphere. For the thermodynamic process, this is constant pressure heat rejection, state 4 back to state 1. Last but not least is overview of proposed modified cycle design. To improve the performance of the existing gas turbine power plant and achieve a thermal efficiency of at least 35%, modifications to the basic Brayton cycle are proposed. The selected improvement techniques include regenerations, intercooling, and reheating, which are commonly applied to enhance gas turbine performance. These modifications aim to reduce fuel consumption, increase network output, and improve overall cycle efficiency. For each proposed modifications, a revised schematic diagram and corresponding TS diagram will be developed to illustrate the change in thermodynamic processes. Detailed performance evaluation and comparison with the base cycle will be present in the subsequent calculation and discussion section.
Assalamualaikum, my name is Amirul Iman. My matrix number is CD240126. So now I will explain the calculation part of our project, which focus on analyzing the performance of BRAYTON cycle and the effect of different improvement technique. To begin with, all calculations are based on several standard assumptions to simplify the analysis. We assume that air behaves as an ideal gas with constant specific heat at constant pressure, and a specific heat ratio suitable for air. The compressor inlet temperature is taken as ambient condition and the inlet pressure is assumed to be 1 bar. The overall pressure ratio of the compressor is fixed and both compressor and turbine operate with given isentropic efficiencies to represent actual operating condition. Lastly, the turbine inlet temperature is assumed to be constant for fair comparison between all the cycles. Alright, next I will explain the base brighter cycle calculation, which serve as our reference case. First, we analyze the compression process from state 1 to state 2. Using the pressure ratio and compression isentropy efficiency, the actual outlet temperature of the compressor is calculated. From this, the compressor work input is obtained. Then, for the turbine process from state 3 to state 4, the turbine entropy efficiency is used to calculate the actual turbine exit temperature. This allows us to determine the turbine work output. The net work output is the calculated by subtracting the compressor work from the turbine work. Finally, the thermal efficiency is determined as the ratio of network output is to heat added in the combustion chamber. For the base Brayton cycle, the results show a network of 229.6 kJ per kilogram and a thermal efficiency of 28.7%, which is relatively low and motivates the needs for performance improvement. Next, we analyze the regenerative Brayton cycle. In this cycle, a regenerator is used to recover waste heat from the turbine exhaust and preheat the compression air before it enters the combustion chamber. The key parameter here is regenerator effectiveness, which relate the actual temperature rise of the compressed air to the maximum possible temperature rise. Using this effectiveness, the regenerator outlet temperature is calculated. Because the air enters the combustor at a higher temperature, the heat added in the combustor is reduced while the turbine and compressor work remain unchanged. As a result, the network output stays the same at 229.6 kJ per kilogram, but the thermal efficiency increased significantly to 38.2%. This value exceeds our project target of 35%, showing that regeneration is very effective in improving fuel efficiency. After that, we analyze the brighter cycle with intercooling and reheating, which mainly aims to increase power output. For intercooling, the compression process is divided into two stages. The pressure ratio is split equally between the stage, and cooling is applied between them to reduce air temperature. This reduces the total compression work, which is lower than that of base cycle. For reheating, the turbine expansion is also divided into two stages, with heat added between the stages. This increases the total turbine work output. When both effects are combined, the network output increased significantly to 351.7 kJ per kilogram. However, because additional heat is added during reheating, the thermal efficiency is lower than that of the regenerative cycle, even though power output is much higher. So now to summarize the calculation result. The base Brayton cycle has low efficiency at 38.7%. The regenerative cycle achieved the highest thermal efficiency of 38.2%, meeting the project target. The intercooling and reheating cycle produce the highest network output of 351.7 kJ per kilogram, but with moderate efficiency. These results show that regeneration is best for improving efficiency, while intercooling and reheating are best for increasing power output. That's it from me. Thank you.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Aris Aikal bin Muhammad Ghazi and my number metric is CD240266. I will be presenting the discussion part of our gas turbine power plant analysis. In this section, I will explain how the different improvement technique affect the performance of a gas turbine based on the BRAYTON cycle. First, looking at the base cycle, the thermal efficiency is 28.7%, which is relatively low. This low efficiency is mainly caused by energy loss in the compressor and turbine due to friction and other irreversibility. In addition, a large amount of fuel is required to increase the air temperature to the turbine inlet temperature, which further reduce overall efficiency. Next, when the regeneration is applied, the performance improves significantly. Regeneration works by recovering heat from the turbine exhaust and using it to preheat the compressor air before it enter the combustion chamber. As a result, less fuel is needed to reach the desired turbine inlet temperature, even though the network output remain the same at 229.6 kilojoule per kilogram. The thermal efficiency increased to 38.2%, which is higher than the target efficiency of 35%. This shows that regeneration is very effective in improving fuel efficiency. Now, moving on the combination of intercooling and reheating, this method mainly focus on increasing power output rather than efficiency. Intercooling reduce the air temperature between compression stage, which is lower than the compressor work from 305.5 kilojoule per kilogram to 253.3 kilojoule per kilogram. Reheating, okay, um, reheating add heat between turbine stage, allowing greater expansion in the turbine. Because of this, the network output increased significantly to 351.7 kilojoule per kilogram. However, the additional heat input causes the thermal efficiency to be slightly lower compared to the regeneration cycle. Overall, this result shows that each improvement technique has a different impact on performance. Regeneration is more effective for improving thermal efficiency and reducing fuel consumption, while intercooling and reheating are more suitable when higher power output is required.
Okay, for the conclusion about our project is this project conclude that the performance of a gas turbine power plant operating on the Brayton cycle can be significantly improved through a combination of thermodynamic optimization and system level enhancement. Analysis shows that the pressure ratio and turbine inlet temperature are the most influential factors, with higher turbines temperature which is within material limits, increasing specific work and an optimum pressure ratio, maximizing efficiency while avoiding excessive compressive work. Improving the isotropic efficiencies of the compressor and turbine reduce internal irreversibility, lowering energy losses, and enhancing overall cycle's performance. The study also confirms that cycles modification techniques including intercooling to reduce compressor work, reheating to increase turbine work, and regeneration to preheat compressed air can collectively raise thermal efficiency, reduce fuel consumption, and improve specific power output. From an operational and environmental perspective, this improvement lower fuel usage and exhaust emission per unit of power contributing to more sustainable energy generation. Overall, optimizing cycle parameters, enhancing component performance, and applying advanced cycle modifications are key to maximize the efficiency, reliability, and economic viability of modern gas turbines power plants.
Okay, as we can see, this is attachment for TS diagram. The left one is the TS diagram for BRAYTON cycle, and the middle one is TS diagram for regenerative cycle, and the right one is TS diagram for intercooling and reheating.